Hey, chemistry, this is part 2 of 2.08. All right, I know I got cut off, but this is the most important sentence probably all semester in chemistry. Atoms want a full outer shell to be stable. So again, all atoms want the outer shell to be full of electrons. Why? So that they are stable. That is the whole reason why they react. That's the whole reason chemistry happens. All right, so let's go over a little bit about the how and the why it happens. So the why is, again, to be stable, and the how. The first orbital can hold 2 electrons. After that, it's full, and electrons start going in the next shell. Yes, they have to go in order from inside out. All other orbitals hold 8 electrons. Yes, there are exceptions, like the transition metals, but we are skipping them for now. So we're just going to focus on the first 2 columns and then the columns on the right-hand side. We are skipping the messy middle transition metals. We'll get to them later. Atoms either gain electrons to get a full outer shell or lose electrons to get rid of the outer shell. Atoms are lazy. They do what is easiest. All right, so if we look at the periodic table, you'll notice that hydrogen has a total of 1 proton. When it's neutral, it has 1 electron. Helium, 2 protons. When it's neutral, it has 2 electrons. Lithium, 3 protons. When it's neutral, it has 3 electrons. The first orbital is full, and now it has just 1 orbital in the second orbital. Well, lithium doesn't want that to happen. Lithium basically says, okay, in order to fill this shell, I would need a total of 8, so I would need 7 more. That is way too much work. It's a lot easier to take this electron, give it to somebody else. Since there are no electrons, this is now the outer shell. And look, it's full because the first shell only needs 2 to be full. So that's how, by losing an electron, that's now the outer orbital, and that is how it has a full outer shell by losing electrons. Okay, same thing right here with this atom. We have 2 in the first shell, 8 in the second shell, and then the 2 leftovers in the outside shell. So this is magnesium. So magnesium is going to say, well, do I want to find 6 more electrons to get a full outer shell? No way, that's way too much work. I'll give these electrons to someone else. Now the outer shell is full. So atoms with 1, 2, or 3 outer electrons will lose the outermost electrons. Now the current outer shell is full, it is stable, it is happy. Woohoo! Atoms with 5, 6, 7 outer electrons will blank the outermost electrons. So look here at fluorine. We see it just needs 1 more to be happy. Gimme, 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 gimme. Oh yeah, that electron's going to sneak right in there. It's got a full outer shell. Look at oxygen. It needs 2 more. Gimme, 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 gimme. Ah, full outer shell, stable. So they are going to gain more outermost electrons. Okay, what about carbon? Carbon has 4. Well, is it going to lose 4 or gain 4? It's actually going to share. So they can share, and we'll talk more about that. Atoms with 8 outer electrons will not react because why not? Helium doesn't either. Why won't neon and argon react? Because they already have a full outer shell and therefore are stable. Okay, we call these diagrams Bohr diagrams, as in after the scientist Niels Bohr. Okay, and we're going to be using these a lot. They don't use them a lot in the lessons, and I wish they did because I cannot stress how much easier this semester is going to be if you understand the Bohr diagrams. So again, the first 2 can go in the first shell, and then you start filling up the other shells, maximum of 8 before you start another shell. If there's only 1, 2, or 3 electrons in the outer shell, they are going to lose the outermost electrons. So the new or current outer shell is full and it's stable. If there are 5, 6, or 7 electrons in the outermost shell, those elements will gain electrons in order to complete that shell. And if they already have a full outer shell, they're already stable, they're done. determine the number of protons, neutrons, and electrons in an ion? Practice finding the numbers of protons, neutrons, and electrons in some ions. All right, so 11 protons is always sodium. But it says how many electrons should there be in the sodium ion described below? Okay, it has 12 neutrons. We don't care about that right now because all I want is a charge of +1. So if my charge is positive, do I need more protons or more electrons? Well, I need more protons. So 11 protons minus 10. 11 minus 10 gives me +1. All right, go ahead and hit pause and get this answer. So I have 17 positive protons. I want a charge of negative. So if I want a negative charge, do I need more electrons or less electrons than protons? Well, if I had exactly 17, my charge would be 0. I want my charge to be 1 more negative, so 18 electrons. So let's look at aluminum +3. If you're having a hard time with these, start neutral. So start at electronically neutral, 13 protons, 13 electrons. I want my overall charge to be +3. So 13 minus what equals +3? Well, if I add more electrons, now it's going to be negative. So, okay, I gotta have less electrons. 13 minus 10 negatives equals +3. All right, so now this one, you're like, wait, they didn't give me protons. Oh, do you remember? How many protons would arsenic have? Well, the atomic number is 33, so it's going to have 33 protons. Let's go ahead and start off at 33 electrons. So now it's neutral, but I want a charge of -3. So am I going to have more electrons or more protons? I'm going to have more negative electrons, and I want 3 more than I have protons. So 1, 2, 3. And beryllium. Okay, they're making you think here. Number of protons is how many? 4, because that's the atomic number. Let's start out neutral. So we have 4. How many neutrons do I have? What's your answer? Well, the mass number is 9. 9 minus 4 is 5. Okay, so that's my mass. And now I want a charge of +2. So do I want more protons or more electrons? I want more positive protons. 4 minus 2 is going to give me a +2 charge. As always, if you have questions, please let me know and let me practice with you. The atoms of some elements can gain or lose different numbers of electrons. So we've been really doing examples of that already. Iron is a good example of how ions of a single element can differ. Okay, so this sentence was like, okay, some atoms can gain 3, some gain 2, no big deal. But now we're going to hit that messy middle transition metals, the ones that I was skipping before right here, where I said it gets kind of messy. Fluorine always gains 1 electron. Oxygen always gains 2 electrons. Nitrogen always gains 3 electrons when they are ionic. Okay, so for now, we're just going to assume it's ionic because we're going to get into how these guys can also share. But for now, the main idea is you know how many electrons it's going to gain or lose. Lithium always loses how many? Just 1. Beryllium always loses how many? 2. Magnesium always loses how many electrons? 2, because that's the electrons in the outer shell. All right, but in the middle, it gets really messy. So let's look at iron. Iron is a good example of how ions of a single element can differ. Iron has 26 protons and 26 electrons when it is electrically neutral. It turns out that iron has a tendency in some situations to lose 2 electrons. But in other chemical situations, iron can lose 3 electrons. So the number of electrons one element can lose is different for the middle messy transition metals. This means that there is more than one kind of iron ion. Iron can exist in 2 ionic states. So you can get iron +2 or iron +3, which again is different. If you look at fluorine, you can only get fluorine -1. That's it. You can only get oxygen -2. That's it. But when you get in the middle, it's messy. You can have multiple choices. Other metals such as copper, mercury, lead, and cobalt also can form more than one kind of ion, as you can see in this table. Any iron plus 2 ion may also be indicated as iron with the Roman numeral 2 in parentheses. And then iron plus 3 would be iron with the Roman numeral 3 in the middle. Other atoms with more than one ionic state are written similarly. So you put, instead of like plus 2 or plus 3, you just put the charge as Roman numerals inside parentheses. So hydrogen is in group 1, charge plus 1. Sodium, group 1 on the periodic table. So group 1 meaning the first group here, charge is plus 1. Potassium, group 1, charge plus 1. Lithium, group 1, charge plus 1. Did you notice the pattern? Yeah. All elements in group 1 will get a plus 1 charge. All elements in group 2 get a plus 2 charge. All elements in group 3 get a plus 3 charge. But then it switches because these share and these are gaining electrons. So all of them in 5A get a minus 3 charge. Oxygen and all of its friends in group 6A get a minus 2 charge. And fluorine and all of its friends in group 7 get a minus 1 charge. All right, but again, let's look at those messy middle transition metals. Silver can be plus 1, it can be plus 2. Iron can be plus 2 or iron can be plus 3. Cobalt can be plus 2, plus 3. Nickel, plus 2, plus 3. Calcium, plus 2. It's in group 2. So that one has to be a 2. And then they went over the other ones on the other side like I did. Okay, so do you need to know which metals have multiple charges? You don't need to know their specific charge. You just need to know that the messy middle transition metals can have multiple charges. So the messy middle transition metals can have multiple charges. All the rest is based on the group. So group 1A has a charge of plus 1, plus 2, plus 3, minus 3, minus 2, minus 1. Electroplating copper. You know what? I feel like we should add that to our notes, what I just said about the groups, because that is super important coming up. So I'm going to add this onto our notes. So I just made a table, the group, and the charge. And again, the reason that it's positive is because it lost 1 electron. Group 2 has a plus 2 charge because it lost 2 electrons. Group 3 has a plus 3 charge because it lost 3 electrons. Group 5, remember we're skipping group 4 because they're sharing. We're going to talk about sharing later. Group 5 has a negative 3 charge because it gained 3 electrons. Group 6 has a minus 2 charge because it gained 2 electrons. And group 7 has a minus 1 charge because it gained 1 electron. Why? Why does it do this? To get a full outer shell and be stable. Okay, again, I know it's a lot of information, so please come see me if you'd like some help with this. That's what I'm here for. Watch the video about electroplating copper. All right, so it's talking about a specific example of how this all matters and how it causes reactions to happen. So watch the video about electroplating copper to see the reaction of copper ions when exposed to different types of charged electrodes. In this laboratory demonstration of electrolysis, copper ions in a solution of copper sulfate react to electric current by forming copper ions that coat negative electrodes. Okay, so because I can't get the sound to show up when I make the video of a video, I do want you to watch it. It's kind of cool. So I will give you extra credit to prove to me that you watched it. So go ahead and watch the video and then email me saying I watched the 2.08 electroplating copper video and tell me like 3 sentences, enough so that I know you watched more than just the beginning and you didn't just skip to the end, okay? Because I watched the video, so write me 3 sentences to prove that you watched the video, and I'll give you a couple extra credit points. And we'll continue this lesson in the next video.